Solving the energy problem is probably one of the greatest challenges facing our society. World energy resources are limited, but our power consumption constantly increases. Measures need to be taken at all levels to develop renewable resources, but also to more efficiently use our available sources of energy. A considerable fraction of all power consumed in our society is related to electricity. Up to 20% of global consumption has been suggested. Consumer electronic equipment constitutes an important fraction of this use, and their energy inefficiency can be as high as 30 to 40%, depending on the field of use. We all know that laptops get warm and the battery charges don't last long and their lifetimes are too short. We clearly need to develop new technology to reduce power consumption in all these areas. Our electronics development includes a wide range of research areas. We explore novel materials, we refine device architecture, and we look for new circuit topologies and increase system integration. Innovation in all these areas will be required to reduce power consumption. In the EU project E2SWITCH, we in particular develop new devices, tunnel FETs and circuits to enable more efficient future electronics for various applications from mobile devices to big data centers. The increasing use of distributed media saved in the cloud has led to the development of data centers with significant amounts of power consumption. Portable sensors will enable at the same time personal monitoring of health and well-being. We combine efforts in fabrication, modeling and characterization to implement the tunnel FETs. It is essential to explore and test new and promising options on the research level prior to their integration into general manufacturing processes. Here our cleanroom facilities within the EU provide important research options that may pave the way for future energy-efficient electronics. We focus on two paths for energy efficiency using either silicon-based technology or 3-5 materials integrated on a silicon platform. The E2SWITCH consortium has been constituted with ambition to realize the productive synergy between partners' expertise and an exhaustive coverage of the competences needed to deliver an advanced energy-efficient switching device. It gathers 9 organizations from a total of 6 different countries. Together they form a unique multidisciplinary network of 4 universities, 1 large industrial partner, 2 research centers and 1 research-intense SME, supported by a dedicated management SME. In E2SWITCH, we target one of the fundamental bottlenecks to power scaling in semiconductor electronics, the transistor drive voltage. For integrated transistors, the ratio between the on-current and the off-current is determined by the drive voltage. This is balanced between performance and static power consumption. To reduce static power consumption, we need to keep any leakage off-current at a sufficiently low level. The balance gives a lower limit to the minimum drive voltage when we want to maintain performance. In modern transistor technologies, we apply about 1 volt and we foresee a development towards 0.5 volt over the next decade. By radically reducing the drive voltage towards 0.2 volt, a 10-fold reduction in energy expenditure may be possible. However, to achieve this goal, innovative new approaches will be needed. In E2SWITCH, we utilize the tunneling mechanism in the transistors to realize what is called a steep slope. In fact, this allows the transistors to be turned off more efficiently to reduce the drive voltage without sacrificing the on-current and thereby balance performance and leakage. One of the key challenges for these so-called tunnel FETs is the physical implementation of the device architecture, the prime target of E2SWITCH. Tunnel FETs rely on xenotunneling in a p-in junction. In the on-state, we have a tunneling path for the carriers that we may close with a gate. We may think of this as a tunnel that we may use for transport instead of climbing over the mountain. The benefit is that we avoid thermal injection over any barrier, as occurs in conventional transistors. The challenge is that the tunneling mechanism lowers the current level and accurate design is thus required to obtain sufficient current levels in the transistor. We focus upon 2 main applications for energy conservation: digital electronics and sensors. Here power savings will help not only to reduce direct power consumption, but devices may also need less cooling. Tunnel FETs may additionally help reduce power consumption in portable sensors with future applications for health and well-being. The inter-chip power reduction, central to this EU project, will not only help make Europe more green, but may also provide new services and devices for us, as European citizens and create a market for new components, devices and systems which will boost these industries in Europe.